Awesome. So hi everyone, welcome to this week's session of Friday. Today I'm going to be presenting evading control flow graph based GNN malware detectors via active opcode insertion method with maliciousness preserving. This is kind of a very interesting extension to a lot of the work that we've actually done at CIC, where we've focused on GNN detection specifically. So this is kind of like the other half that we're going to look at today about how someone might get around that. So a little bit about myself. My name is Griffin Higgins. I'm a PhD student in computer science here at UND. I'm also a cybersecurity software developer here at CIC. And I love nerdy things, as you well know. And I was starting to run out of nerdy things, and then I finally bought myself my first gaming PC ever. So yeah, it also lights up. I'm like, yeah, thank you. It also lights up on like a lot of other things, and I wanted to get it before the AI crash causes all the PC stuff to skyrocket. For some background on the things we're going to be talking about today, I'm actually going to start in a different area. I'm going to talk about cryptology. If any of us are familiar with cryptology, we might understand that there are kind of code makers and they are code breakers. They're the people that do the cryptography, like they make the codes, and then there's people that try and break them with cryptanalysis as the formal term. Today we're going to be talking about this kind of very similar thing, but with respect to malware. And there are lots of different ways we can frame this, but today I'm going to be playing this kind of game between those performing the detection on people making malware. So if I give you some binary file, can you tell me if it's malware or if it's benign? And those same people that are making the malware also trying to get around the people trying to detect them in the same way. And this game kind of looks like this. I know it's kind of extreme, but it's fun. I thought I'd just throw it up from Gemini. But again, we might have like this malware in the middle being this kind of graph of green components, and then kind of this superhero battle between those performing the detection and those performing the evasion. So for those performing the detection, they have lots of different things at their disposal. They can use raw byte sequences of binary programs. They can use opcodes or engrams. They can use binary visual grayscale graphs. But most importantly, they can also use control flow graphs. We're going to briefly talk about what that is in a moment. Also, they have lots of different models that they can use to act on these features or things that we extract from binary data. So they can use convolutional neural networks, they can use recurrent neural networks, or they can use graph neural networks. So that's great. But if we're on kind of the attacker or the evader kind of side of things, we can also do stuff to combat this detection. We can use gradient-based fast gradient sign method attacks. We can also use randomization-based attacks, GAN-based attacks, or something we're going to talk a little bit about today, which is reinforcement-based learning attacks. Some challenges that we face as someone trying to get around detection are that direct modification of the CFGs or the control flow graphs are not feasible. And here I'm not talking simply about like patching a binary or overwriting a single instruction. I'm talking about actually manipulating nodes and edges between them in the graph, because again, this is only something we get after we've kind of decompiled this or reversed this binary program into its graph form. So it's not something we actually really have access to immediately. There's also challenges as they relate to function preserving limitations. So if I write this really evil program and I get it in a binary format, and then I want to go change it, I have to be really, really careful about how I change it, because if I mess up the wrong thing, then the program just explodes and it won't accomplish my evil end goals. There's also difficulty in identifying effective modification positions. Just because I change something or make it some weird gobbledygook in a certain position, it doesn't mean that I'm actually going to evade detection. It just means that I've changed something in the binary. We might have to do more work to actually intelligently evade this kind of detection. So great, that's the kind of higher order game that we're going to be playing today. But some questions you might have left are, what is graph learning and what is a CFG? I actually just talked a little bit about what a CFG is. So I'll just touch on graph learning. Essentially, we often have like tabular data or data in kind of a grid for thinking about images, but not oftentimes this will be nice and structured. Sometimes we might have unstructured data in the form of graphs and relations between pieces of data. We might want to model this and learn on this respectively. So something we can do, in this case specifically, we can employ message passing. So we're going to share information with all of our neighbors. Our neighbors are also going to do that in tandem with their neighbors. And we're going to learn basically how node nodes view their neighborhoods and use those representations to construct how we might look at a graph in high-dimensional space. But if that's too much, don't worry about it. We're just going to use these things and say, given a piece of graph as a CFG to a graph neural network, they're going to tell us if it's going to be benign or malicious. So great. Let's actually dive a little bit into the methodology of the work itself. So in the start, we're going to basically go through the normal detection process that we might have done in some of our projects at CIC. We might go get our data set of benign and malicious samples. We might extract or compute their CFGs respectively. We then might actually vectorize them or create representations. So for each basic block in a CFG, it contains non-branching assembly instructions. If you go and open one up, you would see it. But for each basic block, we want to have something that represents what that node actually is. So that's what's meant by vectorization. After this, we can actually train a graph neural network. And after that, we can take it and use it for detection in the real world. Or if we're an adversary, we can take that same model and do some more things that we're going to do in a moment. So great. Let's say that I did that. Let's say I have this detector, and given CFGs, it will detect if binaries are benign or malicious. We can then go through and start to extract pieces of binary or benign binary sequences, and we can use them as input to an agent, a reinforcement agent, a reinforcement learning-based agent. And here what this agent is going to do is, given some piece of malware that's going to be the environment that this agent is going to act on, it is going to figure out, and we're going to tell it where to insert pieces of benign code. It's going to figure out an optimal strategy for inserting that benign code into the malicious code in such a way that when we run our previous model, that it will be classified as being benign. And it will learn to do this better and better over time. So that's the high level overview of what's going to take place. We can also, so it's going to be the high level of what's going to take place. We can also formalize it with the following algorithm. If we want to come back to this later, that's great, but I have lots of slides, so I want to keep it moving. But this is kind of an important slide. We also want to know what the objective function is going to be, because it is not enough just to insert a bunch of benign things into the program. We also want to make sure that this is preserving the functionality without increasing the size of the malicious binary too much. So, and we also want to measure if we're making any progress towards evading these kind of detectors. So here we have the following equation. F is going to be this reinforcement-based learning algorithm. We're going to take our malicious sample and we're going to give it to this reinforcement-based model. We are also going to get the original malware sample, and together we are going to pass those to some function that's called G. And what this is going to do is it's going to be like kind of the detector, and it's also going to tell us has the malicious probability of detecting this sample decreased since we have made this last change. This is important because if we also measure it against the load increase or how much we've added to the file, the malicious binary file, we might want to oppose those things. So we want to make really good strategic changes. We don't want to just be changing everything willy-nilly. Okay, great. So now we understand a little bit more about what is actually going to be changed and what the strategy is, but how is this technically going to work? So we're going to start off with the following observations. First and foremost, if we have benign samples, we can reverse engineer them, and we can go look at their assembly code, right? We can take that assembly code and we can go and look at different basic blocks that might exist. Later on, we're going to take these basic blocks and inject them, but we can all maybe recall back to our undergraduate courses in like assembly programming languages that here lots of different things might be modifying registers, or they might be modifying like stack pointers, and they might be doing lots of different things. So if I take this piece of benign code and I effectively transplant it into my piece of malicious code, how can I know that when the benign code is running, it's gonna not mess up a bunch of stuff, that when it returns to the malicious code, that the malicious code will continue to execute equivalently to what it would have before? So that's kind of an open question. So here what we're going to do is we're going to go through and we are going to remove any instructions that would otherwise interfere with the registers. We're also going to basically push and pop all the different instructions that would relate to where we're going to return. So essentially, we're just kind of cleaning this to make sure that it's not going to mess up our malicious code once it's been transplanted or injected into it. Great. So, for example, if we had some code, some assembly code, and we had its respective control flow graph on the right-hand side here, we can see that we might first have to go and identify an insertion position. In the work, you can't just insert this piece of benign code anywhere. It has to follow a very specific kind of length for the instruction. So yeah, because effectively we're going to be doing something not unlike inserting an element into a linked list, where if we have some kind of basic block, we're going to have our new benign block, and we're going to link it there, and then we're going to take whatever the tail of that would have been, we're going to link it back to our malicious code. So think of it like we're just doing an insertion into a linked list. But if we do this, we might say with insertion, there would be this kind of new inserted block where we would jump into it and then jump back to what we would have been doing earlier. And again, this block has been cleaned, so it's not going to mess up any of our other code. It might kind of in more detail look like the following, where we might have our original kind of jump position, the new inserted block that we're going to have, it's going to jump back to another position and then keep going forward. And most importantly too, the instruction that we overwrite in order to say jump to this new benign block, we have to keep track of it and we have to add it to the end of the benign inserted new block that we now have control over before it returns to where it would have been, which would be the same position. And again, this is just like the actual edge removing kind of cases, so it very much is like inserting into a linked list. In terms of experimental setup, the authors consider two different data sets, the Sorrel 20 million data set and the BODMAS data set, which some of us are very familiar with. Also, they consider the benign, and those are just where the malicious samples are going to come from. They also consider the benign samples. How am I doing that time? Okay. They also consider the benign samples. Importantly, in a lot of data sets, these are actually harder to get than malicious samples. We might be saying, why? It's due to copyright. So oftentimes, like if you go and you publish a bunch of Windows like executables from somewhere, they don't want you to do that, and no one else is also going to complain if you publish their illegal malware data sets, so you don't have to worry about the legality on that side. But it does impose a huge constraint that whenever we do try to work with binary executable samples and not just features that have been derived from them and subsequently published, that they are usually going to be coming from like the operating system or just popular applications or things like that. So it's good to see that they go out and collect those for themselves. In terms of the data sets, they use the malicious samples from the Sorrel 20 million data set and 8,000 of the benign samples to train the initial defensive GNN to do the classification. Furthermore, they use 2,000 samples for test and 2,500 samples for validation. In terms of training their actual kind of malicious perturbation system, they use 500 samples from the BODMAS dataset and for training it, and 2,000 samples for validation. And all of the benign opcodes that they use to inject into them are selected from the benign validation samples in the previous set up here. So this is important because it means that there's going to be no like cross-contamination between the data sets. It gives us a little more confidence that yes, this is actually going to work on malware samples that we haven't seen before from another data set. So that's a little bit more on that. Also, in terms of the threat model, the defender is the GNN model. I think we covered that a little bit. The attacker in this case is given a sample predicted as malware by the defender to alter. So it's not the case that the attacker is going to have to be like perturbing malicious samples that were already predicted to be benign. That would kind of be silly. So that's the first case. In the next case, the attacker is given black box access to the defender model, specifically predicted probabilities. So all this means is just that the attacker won't know what the internals of the model architecture are looking like. Think about it like if you use like ChatGPT on the cloud, like you can't actually go mess with the model yourself, you just kind of get to submit prompts to it. But the important thing here is that we're assuming that we can get the predicted probability back, because it's not enough to know, is this sample being classified as malware? Is it being classified as benign? We we want to understand, oh, it was classified 99% as malware before, and now it's classified as 70% malware now. That's good for us because we can measure any kind of reduction we're making so that our reinforcement learning agent can actually learn to like minimize that small thing. So even if it's still making malicious predictions, that's okay, as long as it's minimizing the probability over time. Great. So here the authors also consider 3 different GNN models, so that's really good. They also consider several different baselines. One is called Jim malware that they adapt for use with the GNN, which is kind of like a similar setup to what they're doing, even though, spoiler alert, it achieves like really bad results here. They also consider function preserving random insertion. So here they basically just extract like one fixed benign opcode that they just randomly insert into the malicious binaries. So that's the first case. The second case is they randomly pick benign opcodes and then randomly insert them so they can measure like the difference between those two things. And then the last case is they use like random benign opcodes and then they insert them via like hill climbing. So they're just trying to see like, oh, I made a little progress out of this like tree of options I have. I'll keep doing the max, and then I'll keep doing the max, and keep doing the max, and keep climbing the hill, which actually kind of gets good results that we'll see in a moment. So that's good. We can also take a look at the metrics. So here, ASR is the attack success rate. So as someone trying to perform this evasion, I want you to classify my malware as being benign. So that's what that is, and we can measure like how many cases we are able to achieve that. The FPR is not the false positive rate, if I say that, just through it being tattooed on the inside of my brain, please forgive me. It stands for a function preserving rate, because again, it's not enough just for us to misclassify this malware. We also want the malware to retain its malicious functionality, because even if it gets out there, if it explodes, it doesn't matter to us. The last couple of things would be the average growing file size, the average growing basic blocks ratio, and the average growing opcodes ratio. We're not going to focus on these too much, but just know that they're talking about how much do we actually have to increase the size of our malicious binary in order to conduct this kind of evasion. Do we have to get like 50% times the binary or 2%? How much do we have to increase it? Some other technical details you might be interested in would be the static control flow graph generation is done with Radara 2 and visualized with IDA Pro. The malicious functionality preserving is evaluated using like the Windows Sandbox and another system for making sure that malware behavior hasn't changed too much, or that at least it can run afterwards. They use a deep graph library instead of Pi22 metrics, so that's interesting. And then for node representations, a very important aspect of graph learning, they look at this paper of malcom, which considers the byte sequences within each basic block to derive a representation for that block. And then they also consider 1, 2, and 3 n-gram methods, respectively, for each block. So great. We can now take a look at the results. So the first thing I want to show off, instead of just numbers and stuff, is if we have our malicious or our original malicious sample on the far left, and then we perturb it to be that kind of middle sample in the middle, we can compare the differences and we can see them in red. So here we can see all the places where we appended all of the basic blocks that we're going to be jumping to throughout our program. And then we can kind of see where they're called in the little red specks in the middle. I know it's hard to see. If any of you are very interested in it, please come talk to me after. But that's just showing you, like, this is the program before the evasion, this is the program after. So it's not changing like wildly. We can also inspect like just an example from IDA Pro, the graph output, and we can see that in some cases, this is not the entire program, this is just a subset of it. We can see that there is this little basic block that's added here, so we can assess that there has been a real change, which is good. We can also take a look at the average attack success rate. So here for MalAOI, the authors propose it gets like really, really good evasion metrics. In almost 90% of cases, it's able to evade just standard GNN detection, so that's good. We can also see that for the Jim malware, which is kind of similar that they compare it with, it does not do very well at all, which is kind of strange to me. But for the random kind of function insertions and the hill climbing, We can see that the random function insertions don't do as well, but certainly much better than the others. But for the hill climbing, it does a little bit better than those. So that makes sense. It meets our expectations because the hill climbing is kind of this smarter way of inserting the basic blocks. The other ones are random, and I'm not too sure why the gym malware isn't performing as well. Great, but not only that, we want to know like how does the attack success rate change as a function of how many perturbations we make. So if I have to make like 100,000 changes to this file and then I get like 100% success rate, attack success rate, maybe that's not what I want. Maybe I want to be very stealthy and not very easily detectable. So we can think about this as being like a budget. If I only gave you like 200 changes, or if I only gave you 600 changes, like what would the effect be? So here we can see that with MalAOI, after about 200 changes, it just like jumps right up. So that's good to see. We can also see that for the hill climbing algorithm, that they get similar performance up to some number of changes. So that's also interesting. Maybe the reinforcement agent is kind of doing just that at the start and then maybe learning crazier things later on. We can also see that the random insertions don't really seem to make much of a difference if it's just for one type of benign opcode insertion or if it's a dynamic type. And then again, the other one is kind of consistently crashing at the bottom. So I think that this point in particular on the graph is actually very interesting because it means like we're getting significant improvement over just random or closely related methods without having to make very many changes. So maybe this is much more stealthy if we're going to try and detect that someone's actually evading us, or if it's just standard malware. We can also take a look at the function preserving rate. So here, in 85% of cases, we can say that the malware is retaining its functionality and that it hasn't just crashed 5 more minutes. So that's good. We can also take a look at the extra payload, so how much we've actually had to add on to these samples in order for it to do these kinds of evasions. So in 12% or 13% of cases, across all the samples, there's a 13% increase in size. So if I give you some binary, if you make 13% more of the binary's worth of perturbations in the sample, you'll do the evasions with like 90%. So that's very good. I'm going to skip the rest of them because they're not as important. But this should keep you up at night. This is really important. The authors also evaluate the malicious predicted probability change across virus total, which again is an industrial closed-sourced ensemble malware detector, which is just a very fancy way of saying like we don't have access to the detectors, and there's a lot of different ones of differing varieties. And after we make our changes, we're able to drop the malicious probability predictiveness by 20%, which is like, that's not good. And in some cases, for some very specific detectors, we can effectively drop their detection rates to near zero. In this case, they didn't test it with like 50,000 samples. That'd be a lot to just query the API with. So they just used 1,000 samples, but that's still pretty staggering. Here, they also considered adversarial training. I'm going to skip this just because I'm running out of time, but please ask me questions on it. But in conclusion, the authors propose MalAOI to modify malware and evade GNN detection. It achieves a very high attack success rate, on average 93.73. Even after adversarial training, it's still very high, so it's concerning. And they also make this very important contribution, which is that they achieve this 20% malicious probability decrease against virus total, not just some GNN detector that they've already worked with. And to preserve the malicious functionality of the samples, to achieve all of that, they only need to increase the file size by about 12%. So that's the conclusion. Critical review, I'm going to skip, and personal review. I would again stress that the 20% reduction against industrial closed source ensemble detectors is like very good. That's not something I think I could just easily go and achieve. Some small things in the paper were some formatting and typos that I saw that needs fixing. And also, it'd be interesting to see an attack evaluated at a much lower perturbation budget, the kind of that graph where they're all going up earlier, just to see the impact of if you could actually evade someone trying to detect you evading, if that makes sense. So with that being said, these are some of my references. Thank you so much for listening to this highly technical presentation, and I'll take any questions if you have them.